Hello everyone and welcome to our series about teaching maths in the FET phase. But before our panel discussion, let's first start by taking a look at our video where learners are introduced to calculus. This lesson is an introduction to calculus. It uses a parachute jump as the context to help learners to get a real sense of the meaning of the underlying concepts of calculus. In particular, we will look at the meaning of the limit of a function leading to the derivative. The main point of the lesson is the difference between using an average value of something and its instantaneous value. Calculus was invented precisely to overcome this problem of describing changing quantities at exact instants in time. The intended outcomes for the lesson are to explain the difference between average velocity and instantaneous velocity at a point in time, to analyze the graph of the parachute jump that describes how distance changes with time, to plot a graph of velocity versus time from a distance versus time graph, to describe what happens during a parachute jump by analyzing graphs of the rate of change of distance with time and the rate of change of velocity with time during the jump.
We study calculus because it finds wonderful solution to problems otherwise which is virtually impossible to solve. When you watch the comrades or any long distance runners, as soon as they start the race, they press the stopwatches to say, now the race has begun and my time is set. And let's say the race started at 5 o'clock in the morning and they finished the race at one person finished the race at 1 o'clock in the afternoon. What does he do? The moment he finishes the race, he stops the stopwatch. And let's say it was an 80-kilometer race and it took him 8 hours. Now, what do you think is speed?
His time was 8 hours, so it's your time over speed. No, your time, distance over your time.
Distance over time, and that gives us?
Your speed.
That gives us 10 kilometers per hour. Do you think that he ran throughout the race at 10 kilometers per hour?
No.
So, he may have ran faster than that, he may have ran slower than that. But what is that 10 kilometers per hour? It's the average speed. Let's say at a particular time you want his speed. That is called instantaneous speed. Speed at that particular moment. To calculate that, we require calculus. When they hear the word calculus, many of the learners are terrified of that concept. Then I tried to bring in to explain to the students the need for calculus, and it's not such a difficult concept. And therefore, I looked at it from the point of view that they are normally going to use in daily life. Can you just focus your attention on this diagram here, on this picture here?
The class will use the example of a parachutist jumping out of a plane to explore calculus. First, they try to predict what will happen.
Passes through the clouds. The moment he passes through the clouds, he opens his parachute. Right. The question is, you think he'll be traveling at a constant speed throughout?
When he jumps off the airplane, the race will be like more faster or something. And when he opens the parachute will slow him down.
Right, that's a good answer. And also you have the gravitational pull of the earth and you'll move faster, right?
In everyday language, we often use the terms velocity and speed interchangeably. However, in science, they are different. Velocity is a vector indicating both magnitude and direction, while speed is a scalar indicating magnitude only. In the context of the parachute jump, we say speed and mean velocity, but because it is clear the direction is downwards, this will not cause any problems. The class agrees that the parachutist will have 3 phases to his jump: a period of acceleration during the initial freefall, a period of rapid deceleration when the parachute first opens, and finally a period of constant velocity while he floats down to earth with the parachute open. The learners are given a graph that represents the speed of the parachutist during the different phases of the descent. The teacher hands out a worksheet with which they will solve problems related to this parachute jump. They also receive a data sheet which tells them what distance the parachutist has fallen at specific time intervals. The kind of questions that can be answered with the information are: when did the parachute open? What was the fastest speed reached? What was the speed just before landing? What was the total height of the descent? Now, how long was the descent in minutes?
You have a graph, and the other page, you have a table of values. That table of values you see there is going to be based on this problem here. Right? A parachutist jumps off the plane, and he comes down free-flowing until he reaches the clouds. After he passes the clouds, he opens the parachute.
The teacher is leaving the learners to think about the problem a little. They do not yet have the tools to solve the problem. The teacher is trying to help the learners to see the need for the analysis that is to follow.
Look at the table and look at the graph. For 0 seconds, he traveled 0 meters. For 1 second, he traveled 4,90 meters. I want you to find the average speed he traveled from 2 seconds to 6 seconds. You may have to use your calculator.
The learners have to work out the average speed by dividing the change in distance by the change in time.
You can discuss with your group. Let's see. 6 seconds, he reached that distance. 2 seconds was that. That minus that divided by what's the distance in time. Have you got the answer, Anastasia?
32455.
Anybody had a problem? I want you to join those 2 points of the ruler. Join the point where it shows for 2 seconds and for 6 seconds.
The learners have to draw these values on their graphs. The resultant graph will tell them the average speed over the selected time interval. The slope of a graph represents how fast a quantity is changing. The slope of the distance time graph therefore represents the rate of change of distance in relation to time, that is, the velocity.
6 seconds.
To get a more accurate idea of the speed over short periods, it is necessary to calculate an average speed between points that are closer together.
Let us look at the distance covered, the average speed covered between 5 seconds and 6 seconds. Anybody's got that answer?
26.92.
26.92. What is the average speed between 5.6 seconds and 6 seconds? Who's got the answer to that?
17.5.
The average speed between 5.8 seconds to 6 seconds. Who's got that answer? 3.12? 15.6. What are we doing each time? We're reducing the time, right? We're making the time as small as possible.
Using smaller and smaller time intervals brings the result closer and closer to instantaneous speed. The learners will now use the skill they have just acquired to approximate the speed of the parachutist at specific points. They have been asked to find the fastest speed reached just before the parachute opens, the landing speed, the average speed of the total descent period, the average speed of the free fall period, the average speed during the period of the parachute opening, and the speed exactly 1 second after the parachute has started opening. They proceed to work on this problem in groups, while the teacher assists those who are experiencing problems.
Okay. The average speed of the free fall period, average speed, how will you work it out? From there to there he's falling, because he didn't start falling from 1 second. He started before. Okay. Let's look at answer to question 1. The fastest speed reached just before the parachute opened.
19.16.
19.16. Right? Okay. The landing speed.
For each of these answers, the learners need to use the formula change in distance over change in time. For the most accurate estimate of a particular speed reached, that is the speed just before the parachute opened, they need to use the smallest possible interval.
The average speed of the free fall period, Salma?
172.47. And I subtracted 4.90. No, sorry, sir. 0.00.
Right.
All over 8.
Right.
And it gave me an answer.
Why over 8? 9 minus 0 is? 9, not 8.
Okay.
Because the distance traveled from 0 second to 9 seconds is 172.47. Can you look at it? And what's the time interval? 9 seconds, over 9 seconds.
The instantaneous speed is the exact speed the parachutist was traveling at a specific moment. To arrive at this speed, learners need to evaluate the exact slope of the distance versus time graph at specific times. Learners first need to complete the table on the right with the most accurate estimate of the speed of the parachutist at the times shown. They then plot the points they've identified on a speed-time graph. It is vital that learners understand the difference between average values and instantaneous values. An instantaneous value of something that is changing only exists for a small instant. Instantaneous values can be seen as average values over a very small time period, or an interval that is very close to 0. The slope of a graph represents how fast a quantity is changing. The slope of the speed-time graph therefore represents the rate of change of speed in relation to time, that is, the acceleration.
We are now going to round up with what we have done. We have realized that to work out instantaneous speed, we have to bring in calculus.
The teacher concludes that instantaneous speed cannot be measured. What we can do is to calculate the average of increasingly small intervals to approximate exact speed. Thus, calculus is the use of mathematics to approximate an ever-changing instantaneous value. The learners have experienced the essential concepts of differential calculus without the aid of theoretical rules.
Now, for an exercise you have to do at home is 1.5. You have to work out your speed. Look at the table partly completed for you. The time intervals are completed. You have to work out the speed and plot those points against speed versus time, the graph. Will you do that? And it's due tomorrow. See, calculus greatly enhances the use of mathematics. And when we do the basic things in school, as far as your limits, your differentiation, and drawing of graphs and interpretation of graphs, it gives them a sound background, basis to pursue the subject at university level.
And now that we've seen our video, time for us to welcome our guests. We've got Smangaliso Twala, who's an independent maths consultant, Mera Hockman from the Wits School of Mathematics, and Catherine Hunter, who's also an independent maths consultant. Thank you very much for joining us. The first question, starting with you, Mera, do you think the parachute jump was appropriate to use in the introduction of calculus?
I think the example was a fine example, mainly because we saw acceleration, distance, time, and velocity in various stages. You know, usually one sees a regular graph which isn't as informative as the graph of this particular parachute jump. So I think it is a nice equation. The graph is interesting and it opened up many questions. So I think, yes, it's a fine example to bring the idea of calculus into the classroom and to attempt to come to some conclusions.
Okay, Smangaliso, would you agree?
Yes, I think I would agree. In most cases, when calculus is introduced, you just see the graphs, and these are not related to anything in reality and in real life. And in this particular instance, the learners were relating the graph and actually plotting a graph themselves, and they could actually see and they can actually tell. This is where the parachute was actually moving fast, and this is where it was slowing down, and the graph can actually show that.
Catherine?
I thought it was a wonderful example. I think it could have been extended in the sense that the teacher needs to ask the question, why would anybody ever need to know the speed at a particular point? Or why would you need to know the average over a certain interval? I think it would be important to bring out a variety of life situations where the same question would be asked. So I think it is a wonderful example. Unfortunately, we can't all jump out of planes, much as it's quite exciting and for learners. But I think it is important to ask that question, why? Why would anybody ever need to know?
Do you think the lesson was an effective introduction to calculus?
A great example again, but only thing that one needs to emphasize is that calculus is about rate of change. It's about finding a slope, a ratio of rise to run. And that's the formative idea that underpins all of calculus. So yes, the example was great to introduce the idea that these rates of change changed because of the parachute. And what is a rate of change? It is a ratio. It is a ratio of what? And that brings you back to the slope and eventually to the tangent. So there is a run through the ideas which needs to be completed by the teacher, because ultimately we're going to get back to the idea of the slope, the tangent, the gradient, etc. So the ideas need to be linked. But the ultimate idea of calculus is that we're finding rate of changes, yes.
Catherine?
I thought there were some very important words there that needed extra emphasis. The teacher did start off by saying we're going to predict. They used that word predict. What is the speed going to be at a particular point? And he showed how difficult it would be, in fact, to predict, and showed how you would use averages and decrease the range to be able to predict. But I think also preceding that, it would be important to emphasize what does it mean to estimate. I thought estimate was almost a subliminal concept that learners would need to be able to give attention to in order to be able to understand this as a backup, and also extrapolation. Those two concepts, which are related to interpreting line graphs, might have been useful to go over and to talk about how they would relate to this particular point. How is it that we can hone in on one particular point using the information that we can glean from surrounding points, given that a line is a collection of points ultimately, and how can we work out the ratio at a particular point using surrounding information? That was in effect what they were doing.
And where do you think the teachers should go from here in teaching the learners about calculus?
I thought it would be quite important, again, as we've said in previous videos, that the learners would need to be able to put it into their own life context to make it meaningful to them. So you could throw it out and for one thing, broaden the scope of varieties and examples of types of where in life they would come across a situation where they might need to use calculus. So on the one hand, getting learners to provide examples, but also getting learners to tease out examples provided by a teacher, and to be able to take further the lessons that they have learned from this particular lesson.
Okay. Mera?
Yes, well, calculus is our great tool in mathematics, and its power must come through to the learners. After addition, subtraction, division, and multiplication, the calculus is our armor with which we fight the world. And this idea must come through to the students, that we couldn't get onto the moon, we couldn't launch our spacecraft, we couldn't do almost anything without this great tool. So once we see that rates of change are prevalent in our lives, and we bring it in and we formalize it, then we get the power of the tool. And then we've got to show, here you've got something that's really great, and you can use it here, here, and here. So again, closing the cycle, taking from your everyday experience, formalizing it in mathematics, and then showing how powerful this tool is.
I would say the teacher would have to use this tool more often now, take more examples that are related to this one, and let the children get used to the idea of solving problems like this, which are actually in real life from their real situations, and that will actually make them know the concepts much better.
Okay. And the teacher's strategy in the lesson, what do you think of that?
I have one problem with it. As I said at the beginning of this little interview, the great parachute idea was that it provided us with a great graph. And from that graph, a lot could be discerned without any statistics, without any other knowledge. You know, just to ask the students, what do you think about this graph? Where do you think the changes happen? By just looking at it, where do you feel that there's a change? And unfortunately for me in this lesson, the statistical analysis took paramount position, while the graphical representation sort of took us backstage. And I prefer the other way around. The graph is something the students can see. It's the whole story at once. Whereas the statistics are bits and pieces, and they've got to put it together. The graph tells the story, and the teacher, I think, could have used that graph to hypothesize, where do you think the change is, what do you think is happening here, and then to verify it using the statistics.
Catherine?
I think that it was a wonderful lesson. There was certainly a fair amount of consolidation that still needed to happen. For example, the teacher presented two different graphs, one showing speed and distance of the fall in relation to speed, in relation to time, and the second graph was showing points that compared the time to speed. And those two different graphs showed different information but could very easily be confused in the minds of the learners and how they related to each other. And I think it would be quite important for the teacher to really go deeply into how the second graph arose out of the first one, and how the very points of change that Mayra was referring to can be found in both graphs, in fact. And that was the one thing. The other thing is to do with, again, the visual, leaving a visual impression and getting learners to trust their interpretation and their instincts, as it were, in relation to interpreting a graph, I think is an incredibly important skill to consolidate. And the teacher would need, I think, to draw out more firmly from learners how they could interpret a wide variety, and certainly not stop at this one graph, but provide lots of examples for learners to get their teeth into.
Mayra?
Yes, just to emphasize that one can look at calculus as an algorithmic procedure, you know, differentiate this, differentiate that. And I really would like to emphasize that calculus is about geometry, and the two must go hand in hand. And that if you teach calculus as an algorithmic method of doing something, you're going to lose its beauty, you're going to lose its value. It's about geometry, it's about behavior, it's about change. And just to underscore that when we teach calculus to novice users.
Okay, thank you very much for your input. That's Mangaliso, Mayra and Catherine. And to our viewers at home and at schools, thank you very much for joining us. Do join us again for Module 25 coming up soon. Goodbye.